Deep within the constellation of Boats, 146 light-years from our solar system, a sun-like star holds a secret that is currently reshaping our understanding of planetary statistics. This is the story of HD 137,010, a star that has quietly orbited the galactic center for billions of years, unnoticed by the naked eye, yet now the focus of intense scrutiny. We have long searched for a second Earth, a twin planet where the conditions for life might mirror our own. However, the discovery of the exoplanet candidate HD 137,010b suggests that the path to finding life may not be a binary yes or no, but a complex calculation of probabilities. This world exists at the very edge of our detection capabilities, a shadow crossing a distant sun, challenging astronomers to define exactly what it means for a planet to be habitable. As we peel back the layers of data from our most advanced observatories, we find ourselves facing a world that sits on a cosmic knife edge, where the presence of liquid water, the fundamental solvent of life, is a statistical toss of a coin. Before we dive into the complex mathematics of this distant world, we must test our understanding of the cosmic Goldilocks zone. In the search for life, astronomers focus heavily on the habitable zone, but this region is not a fixed physical boundary. It is a calculation based on a star's luminosity and a planet's orbital distance. Here is your scientific challenge for today. If a planet is found within the optimistic habitable zone of its star, does this guarantee that the planet has a solid surface and an atmosphere? Think carefully about the relationship between orbital mechanics and planetary composition. The answer, which reveals a fundamental truth about how we categorize exoplanets like HD 137,010b, will be explained in detail at the conclusion of our journey. Pay close attention to the data points regarding planetary mass and density discussed in the coming minutes. The detection of HD 137,010b did not happen with a sudden visual confirmation, but through the painstaking analysis of radial velocity and transit data. Astronomers observed subtle wobbles in the host star's motion, caused by the gravitational tug of an orbiting body. This planet is not a small, rocky world like Earth, nor is it a massive gas giant like Jupiter. It occupies a mysterious middle ground. Data suggests a world that is significantly more massive than our home, likely a super-Earth or a sub-Neptune. Its year, the time it takes to complete one orbit, places it precisely where the stellar. Radiation is neither too intense to boil away oceans, nor too weak to freeze them eternally. Yet the word candidate remains attached to its name. In the rigorous world of peer-reviewed science, a single observation is never enough. We are currently in the stage of verification, using the transit method to confirm its diameter and atmospheric potential, ensuring that what we are seeing is not stellar noise, but a true planetary neighbor. What makes HD 137,010b particularly fascinating is the recent statistical modeling applied to its orbit. Unlike many planets that are clearly inside or outside the habitable zone, this world sits in a transitional state. Scientists have calculated two distinct probabilities: a 40% chance of residing in the conservative habitable zone and a 51% chance of being in the optimistic habitable zone. These numbers represent a breakthrough in how we communicate uncertainty. The conservative zone assumes a planet must have an atmosphere similar to Earth's to maintain liquid water. The optimistic zone, however, accounts for different atmospheric compositions, such as higher levels of greenhouse gases that could keep a planet warm even further from its star. At 51%, HD 137,010b is essentially a cosmic coin flip. It represents the limit of our current models, a world that could be a frozen wasteland or a humid, water-drenched paradise, depending entirely on the chemistry of its air. To understand why a 51% chance is so significant, we must look at what scientists call the essential ingredients. Liquid water is the primary focus, because it acts as a universal solvent, allowing complex organic molecules to interact. However, water alone is not enough. A planet needs a protective magnetic field to shield its surface from lethal stellar radiation and a stable atmosphere to provide pressure. For HD 137,010b, the mass of the planet plays a crucial role. If it is too massive, it may have retained a thick envelope of hydrogen and helium, turning it into a mini Neptune with crushing pressures and no solid surface. If it is rocky, its gravity might be strong enough to hold on to a dense atmosphere, potentially creating a runaway greenhouse effect like Venus. The quest now is to move beyond where the planet is and discover what the planet is. We are looking for biosignatures gases like oxygen, methane, and carbon dioxide that, when found together, could indicate the presence of biological processes. Our ability to study HD 137,010b relies on a leap in technological capability. While the Kepler and TESS missions provided the initial hints, the James Webb Space Telescope and future missions like the ESA-ARIEL are the keys to unlocking this mystery. These instruments do not see the planet in the traditional sense. They perform transmission spectroscopy. As the planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere. By analyzing which wavelengths of light are absorbed, scientists can identify the chemical fingerprints of water vapor, nitrogen, or even complex hydrocarbons. This process is incredibly delicate, requiring the telescope to maintain absolute stability while staring at a point of light trillions of miles away. The data from HD 137,010b is still being processed and debated. Each new photon of light collected is a piece of a puzzle that could eventually tell us if we are looking at a sterile rock or a world with a sky very much like our own. It is vital to distinguish between a habitable zone candidate and a habitable world. In the media, discoveries like HD 137,010b are often sensationalized as Earth 2.0 found. However, the scientific reality is far more nuanced. Many planets in the habitable zone are tidally locked, meaning one side always faces the star in eternal day, while the other is trapped in a permanent frozen night. Others may have been stripped of their atmospheres by stellar flares early in their history. HD 137,010b serves as a reminder of the Great Filter, the many obstacles that a planet must overcome to actually support life. We must embrace the uncertainty of the 51% statistic. It is not a failure of science, but a triumph of precision. We are now able to quantify our ignorance, identifying exactly which worlds deserve our most expensive and limited telescope time. HD 137,010b is a prime target, not because we are sure it has life, but because it sits exactly at the boundary of our current understanding. As we conclude our investigation into HD 137,010b, it is time to return to our quiz. Does being in the optimistic habitable zone guarantee a solid surface and an atmosphere? The answer is no. The habitable zone is strictly a measure of distance and heat. A planet can be in the perfect location, but be a gas giant with no surface to stand on, or a naked rock with no atmosphere to trap heat. HD 137,010b remains a mystery because we have the location, but not yet the composition. If it proves to be a rocky world with a stable atmosphere, that 51% chance could become the most important discovery of the decade. But regardless of the outcome, the study of this world brings us one step closer to answering the ultimate question. We invite you to join us on this frontier. Subscribe to Next Frontier Science, like this video to support rigorous scientific communication, and comment below. Do you believe the first life we find will be on a super-Earth like this one? The search continues, and the data is just beginning to arrive.